In previous lessons, we divided a region of integration into subrectangles. These aren't the only shapes we can use. In this lecture, we will divide the domain into regions called polar rectangles. A polar rectangle is a region in R2 that is a rectangle in polar coordinates. That is, a region R is a polar rectangle if in polar coordinates it has the form theta 0, theta 1 times r0, r1. For example, the region that is in between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4 and angles between pi over 6 and pi over 3. In polar coordinates, this is pi over 6, pi over 3 cross 1, 2. Another way to think about a polar rectangle is that it is just part of an annular region. Remember, an annular region is a region between two circles. Let's say we want to integrate the function f over this region here. This region is a polar rectangle. So far, we've used rectangular coordinates, which means we divide the domain into a bunch of rectangles, and for each rectangle, we multiply f evaluated at some point in that rectangle times delta x, delta y, which is the area of that rectangle. And then we add this up for k equals something to 1 to something and j equals 1 to something. In this case, it would be k equals 1 to 10 and j equals 1 to 10. Let's look at that same region, but from a polar perspective. So it's the same region that I've outlined. And now what we want to do is for each rectangle, we want to evaluate f at some point in that rectangle and multiply it by the area of that rectangle. Now when I say rectangle, I mean polar rectangle. So to do this is going to be f, not of x, it has to be in polar coordinates. So we could say x, rk, cosine theta j, rk, sine theta j, times delta a kj, where the rectangle kj is just how I'm indexing these polar rectangles. So approximately, what is the area of this rectangle that I've colored in here? Well, let's kind of put it off to the side here. So what approximately is the area of this rectangle? Well, if the coordinates of that point are r theta in polar coordinates, then the coordinates of this point are r plus delta r theta, and the coordinates of that point are r theta plus delta theta. This is not a rectangle. This is a polar rectangle, but is not an actual rectangle. But as we get more and more polar rectangles, as we divide this region up into smaller and smaller rectangles, it becomes closer and closer to an actual rectangle. And so we can approximate the area as if it were a rectangle. So it's approximately going to be the product of the length of that times the length of that. The length of that is exactly going to be r times delta theta, because it is the arc of a circle of radius r going through delta theta radians. So the length of this is delta r, the length of this is r delta theta. So if we're treating this like a rectangle, the area is going to be the length times the width, or r delta theta. So we can write this as f of rk cosine theta j, comma, rk sine theta j times rk delta rk delta theta j. So in other words, if we evaluate f at some point in that polar rectangle, say at the point rk cosine theta j, comma, rk sine theta j, and then multiply by the area, and then add all of this up for all k and j values. This is approximately going to be the integral of f over the region. Now, as k and j, as we get more and more of these polar rectangles, this is going to go to a double integral. R is going to go from r0 to r1. Theta will go from theta 0 to theta 1, and the function that we're integrating is f of r cosine theta, r sine theta, r dr d theta. This extra r comes from this r right there. Now, depending on what the problem is, you have to figure out what r0, r1, theta 0, and theta 1 are. And just like we saw in rectangular coordinates, the limits of the inner integral could depend on the variable of the outer integral. I hope that as we look at some problems over the next few videos, this will become clear, and you'll come back to this video.